Have you ever, actually watched a SpaceX Falcon 9 booster land upright at Cape Canaveral?
Oh, man. I mean, it's unforgettable.
Right. If you have, you know exactly the feeling I'm talking about. You're watching this massive, glowing, 12-story pillar of metal just descending from the sky.
Yeah, falling backward, basically.
Exactly. And the landing legs fold out at the very last possible millisecond, and it just sits down on a pad of concrete. When you watch it, there is this undeniable weird glitch in your brain.
Oh, absolutely. It violates our intuitive sense of gravity and momentum, you know?
It really does. It almost looks fake.
Yeah.
It feels like you're watching a science fiction movie, but someone accidentally left the footage playing in reverse.
Yeah, because we are, fundamentally conditioned to see massive falling objects crash, not land.
Right. And that's the mission for today's deep dive into Aaron Rose's August 2026 article in Tech Reader magazine, which is called The Age of the Returning Rocket.
It's a fantastic piece.
It really is. We are going to deconstruct exactly why that image feels so deeply uncanny to us. And, unpack the truly staggering engineering it takes to bring a building safely back from the edge of space.
Which is no small feat.
Not at all. But beyond just the mechanical nuts and bolts, we want to explore how this one visual, a rocket landing on its tail, signals a monumental shift in our entire relationship with the cosmos.
It's a total paradigm shift.
Okay, let's unpack this. Because to really grasp why this machine returning to a concrete pad is such a marvel, you have to look at the sheer absurdity of how we treated spaceflight for the previous 60 years.
Yeah, I mean, the defining economic principle of the early space age was, quite simply, astronomical waste. The entire paradigm was built around discarding the vehicle.
Aaron Ruse uses this striking analogy in the article to highlight this, which I just love. He says, to imagine you are an aerospace company, right? And you spend years designing this state-of-the-art jumbo jet. It is an absolute masterpiece of modern engineering. You fill it with incredibly complex engines, avionics, structural components, all of that.
Costing a fortune.
Right. You load up your passengers or your cargo, you fly the plane exactly one time, and then you purposefully ditch the entire aircraft into the middle of the ocean.
Just throw it right in the water. And then you go back to the factory and build an entirely new jumbo jet from scratch for your next flight.
Which sounds completely insane. You do that every single time you want to fly anywhere.
It really is wild when you frame it like that.
You are throwing away tens, sometimes hundreds of millions of dollars per launch. And for decades, this brute force method was just accepted as the norm. It was just the immutable cost of doing business in space.
Yeah, rockets were basically disposable monuments. They had their 3 minutes of glory, and then they became ocean trash or orbital debris.
But I mean, why did we do it that way for so long?
Well, the engineers building those early rockets, they didn't lack imagination. The desire for reusability existed at the very dawn of the space age.
They wanted to reuse them.
Oh, for sure. The problem was that the physics involved were just incredibly punishing. A rocket is not an airplane taking off and gliding back down to a runway,
Right. The speeds are totally different.
Exactly. A rocket travels at hypersonic speeds, hitting these crazy velocities required to push payloads into orbit. When it comes back down, it endures blistering heat from atmospheric friction.
Which airplanes just don't have to deal with.
Right. And crucially, it has to somehow shed thousands of miles per hour of velocity before it can safely return to the surface of the Earth. The idea of a rocket gracefully landing upright on a column of fire wasn't just difficult.
It was impossible.
Well, it was largely dismissed as a thermodynamic and aerodynamic fantasy.
Right. Until December 2015. That was the turning point when a Falcon 9 booster finally returned from space and touched down safely.
A huge moment.
Huge.
Yeah.
But what the article points out, and I think this is a really crucial shift in perspective, is that this historic moment wasn't actually a surprise to the people paying close attention to the industry. It was an inevitability.
Yeah, the space industry had effectively reached an economic breaking point. The old model of throwing away the vehicle every single time was fundamentally capping human progress.
It was just too expensive to keep doing.
Precisely. Reusability was no longer just some futuristic optional feature. It was the only logical path forward to save and expand the industry.
Because without it, space would just forever remain this boutique domain reserved for governments and billionaires, instead of like an accessible, scalable frontier.
Exactly. But the physical hurdles, the hypersonic speeds, the insane heat, the gravity, those were always there.
Right. The laws of physics didn't magically change in 2015 to suddenly allow for this. So it clearly wasn't just aerospace companies building a stronger metal tube. It wasn't purely a hardware revolution.
No, not at all. The physical engines are incredible, obviously. But what's fascinating here is that the breakthrough that actually solved the landing problem was autonomy.
Autonomy. Okay, let's contextualize the sheer physical difficulty of what this autonomy is actually dealing with.
Please do.
A Falcon 9 booster is a cylinder roughly 12 stories tall. So to you listening right now, I want you to imagine trying to parallel park a 12-story apartment building.
Which is hard enough.
That's hard enough, yeah. But now imagine that apartment building is actively falling out of the sky at thousands of miles an hour. You have to park it perfectly while blindfolded, and you are being buffeted from all sides by completely chaotic, unpredictable wind shear.
That is a perfect analogy, and the reality is no human pilot could possibly fly that descent.
We just aren't fast enough.
Not even close.
Yep.
Human reaction times, the milliseconds it takes for a visual cue to reach the brain and translate to a physical hand movement on a joystick, they are far too slow to handle a 12-story structure falling through chaotic aerodynamics.
The rocket just has to fly itself.
It has.
So we are essentially talking about a 12-story, supersonic, self-driving car.
Right.
How does it actually perceive its environment while it's falling?
It relies on an incredibly sophisticated guidance system built around sensor fusion.
Sensor fusion, okay.
Yeah, the rocket's brain is constantly pulling in disparate streams of data. You have GPS giving positional data. You have gyroscopes measuring the vehicle's exact tilt and orientation in three-dimensional space.
Wow, okay.
Plus, accelerometers are measuring the physical forces of speed and direction, and pressure sensors are reading the dynamic atmosphere outside the hull.
But wait, all of those sensors have flaws, right?
Yeah.
Like GPS has a slight lag.
Yeah.
It tells you where you were a fraction of a second ago, not where you are right this exact millisecond.
Yeah, and that lag is exactly why sensor fusion is so critical. The algorithms running the system have to mediate an argument between all these different senses. Yeah, like the GPS might have a delay, but the accelerometers register an immediate shift in momentum if a gust of wind hits the rocket. The algorithms weigh the reliability of each sensor in real time, fusing the data to predict the rocket's own motion into the future.
Oh, so it's predicting where it's going to be.
Exactly. It anticipates atmospheric disturbances before they can knock it irreparably off course. It's correcting its trajectory hundreds of times every single second.
This is insane.
The software architecture here is far closer to advanced robotics than traditional old-school ballistic aerospace control systems. During that descent, the booster completely ceases to be a dumb machine following a pre-programmed arc. It becomes an active pilot.
Okay, so we have this supercomputer brain making hundreds of split-second calculations. But a brain still needs muscles to actually physically steer the body.
Right, it needs to move.
And as it falls back to Earth, it moves from the complete vacuum of space down into the thick, soupy atmosphere. Obviously, the physical environment changes drastically, so the steering mechanism has to change too.
Right, completely change it.
Because when the rocket first separates from the upper stage, it's basically in the vacuum of space. There's no air, so you can't use wings or fins because the steering wheel doesn't work if there's no air to push against. How does it flip itself around?
Up there, it relies on cold gas thrusters. These are small pods near the top of the booster that shoot out highly pressurized nitrogen gas.
It's shooting gas out into space.
Exactly. In the vacuum of space, those little bursts of gas provide enough reactive force to pivot the massive rocket. The brain fires these thrusters in precise sequences to flip the vehicle around so the engines are facing the direction of travel and to stabilize its roll.
Getting that orientation locked in must be critical.
It's life or death for the mission. It has to be perfectly positioned for the aerodynamic violence that comes next.
Because as it falls further, it finally hits the atmosphere. And this is where it deploys my absolute favorite piece of engineering in the whole system, the titanium grid fins.
Oh, the grid fins are brilliant.
The source article describes them as looking like waffle irons, which is incredibly accurate. They are blocky metallic grids that fold out from the sides of the rocket near the top. But when you think of aerodynamics, the mental image is always a sleek, curved airplane wing.
Yeah, totally.
So why would aerospace engineers use a blunt, drag-inducing waffle iron to steer a supersonic vehicle?
I know, they look completely counterintuitive to traditional flight. But the aerodynamics of a grid fin are uniquely suited for this specific chaotic environment.
How so?
Well, a traditional sleek airplane wing is designed to generate lift during horizontal flight at relatively stable speeds. But this rocket is falling backward and its speed is changing dramatically. It hits the atmosphere at supersonic speeds, eventually slowing down to subsonic speeds.
And a traditional wing would struggle with that transition.
Oh, a traditional wing would likely become useless or just be ripped apart. At supersonic speeds, air doesn't behave like a fluid. It acts almost like a solid wall.
Wow, a solid wall of air.
Yeah, so a sleek wing would build up a massive bow shockwave that could completely disrupt the airflow over the control surfaces. It would render the rocket unable to steer. Grid fins solve this. The intersecting blades allow the supersonic air to flow right through the grid rather than just slamming into it.
Oh, I get it. It's literally letting the air pass through the waffle squares.
Exactly. By subtly pivoting these waffle iron structures, the rocket's brain manipulates the shock waves and the airflow to control pitch, yaw, and roll. They maintain control authority across that whole turbulent transition from supersonic to subsonic flight.
So they act less like the wings on a glider and more like the fins on the back of a dart.
That's a great way to put it. They turn a 12-story empty aluminum can into a massive precision-guided dart. They angle the booster toward the landing zone, constantly pivoting to counteract the wind shear, trying to push the rocket horizontally.
Because without them, it would just blow away.
The article notes that without those grid fins actively flying the vehicle through the atmosphere, the rocket would drift miles away from the intended landing pad.
So we have the brain crunching the sensor data, the nitrogen jets flipping it in the vacuum, and the waffle iron grid fins steering it through the wind like a dart.
It's a beautifully orchestrated dance.
It is. But surviving the reentry and actually stopping this massive object is a whole different physics problem. When I was reading the section on the reentry burn, I had to stop and reread it because the logic feels entirely backwards.
It catches a lot of people off guard.
Here's where it gets really interesting. I have to push back on the logic of this maneuver. Because, okay, the rocket is plummeting toward Earth, slamming into the thickening atmosphere at hypersonic speeds. The friction from the air is so intense that it's generating extreme heat, literally forming a sheath of superheated plasma around the bottom of the vehicle.
Right, a literal fireball.
Yeah. And the rocket's response to this oncoming wall of fire is to turn on its own rocket engines and fire them directly into the oncoming plasma. Why would you ever do that? Doesn't fighting friction fire with rocket fire just create a much bigger fire? It feels like you're just begging to melt the engine bells.
It sounds completely contradictory, I agree. The instinct is that adding more energy to an already superheated environment would just lead to structural failure.
Exactly.
But this counterintuitive move is a stroke of engineering brilliance to avoid a massive weight penalty. The alternative to the re-entry burn is using heavy ablative heat shields, like the thick tiles on the space shuttle or the Apollo capsules.
Oh, like covering the bottom in heavy armor.
Right. But every single pound of heat shield you stick on the bottom of a booster is a pound of payload you can't take to orbit. It's dead weight.
So they use the engines to solve the heat problem instead of adding heavy tiles.
Yes. By firing the engines into the oncoming hypersonic airflow, they accomplish two things simultaneously. First, the incredible thrust violently decelerates the rocket, bleeding off a massive amount of kinetic energy in a very short time.
Okay, that makes sense. Braking.
And second, that high-pressure plume of rocket exhaust actually acts as a physical barrier. It pushes the supersonic shock wave away from the vehicle, creating a sort of protective, cooler aerodynamic bubble ahead of the rocket's structure.
Oh, wow. So by thrusting into the fire, they slow down the vehicle so rapidly and push the plasma far enough away that the friction fire never gets the chance to melt the metal.
They literally use fire to survive fire, but the margins are incredibly thin here.
I can imagine.
If the algorithms burn the engines too long, the rocket wastes precious fuel it desperately needs for the final landing phase. If the burn is too short, the vehicle comes in too hot, the aerodynamic bubble collapses, and the atmospheric friction compromises the structural integrity of the booster.
It just melts. So, assuming it survives the reentry burn, it continues falling through the lower atmosphere. The grid fins are twitching and steering, the ground is rushing up fast, and this brings us to the final maneuver, which is the landing burn.
The famous hover slam.
Yeah, the article specifically calls this a hover slam. I think a lot of people picture a rocket landing like a helicopter. You know, they assume it comes down, slows to a stop 50 feet in the air, hovers for a second to center itself, and then gently lowers down.
That's the sci-fi movie version of it.
Exactly. But the physics of a Falcon 9 make a true hover physically impossible.
Right, entirely impossible. It comes down to a fundamental metric in aerospace called the thrust-to-weight ratio. A Falcon 9 has 9 Merlin engines at the base. To land, it only needs to fire a single center engine.
Just one.
Just one. But that one engine is spectacularly powerful. And at this late stage in the flight, the booster has burned through almost all of its heavy liquid oxygen and kerosene propellant. It is essentially just an empty, lightweight, 12-story aluminum tube.
Because all the mass is gone. It burned it all on the way up.
Exactly. The mass is gone, but the engine's power remains. Even if the flight computer throttles that single Merlin engine down to its absolute lowest possible setting, which is about 40% of its maximum thrust, that 40% still pushes upward with more force than the entire empty rocket weighs pushing downward.
So its thrust-to-weight ratio is greater than 1.
Exactly. And anytime your thrust is greater than your weight, you cannot hover. You are mathematically accelerating upwards.
So if a Falcon 9 tried to pause and hover in midair, it would immediately just start flying back up into the sky.
Yeah, it would go back up.
So it can't brake early and coast down. It has to time the braking perfectly.
And that is the hover slam. It is a highly controlled fall. The rocket's radar altimeters are pinging the concrete pad, constantly updating the distance to the ground.
Just feeding that data to the brain.
Right. And the algorithms calculate exactly when to ignite that single engine. The aggressive deceleration has to bring the rocket's velocity to absolute zero at the exact millisecond the landing legs make contact with the concrete.
The timing has to be absolutely flawless. I mean, if the engine ignites a second too late, the rocket slams into the pad before it can shed its speed.
It crashes.
And if it ignites a second too early, it reaches zero velocity while it's still 50 feet in the air. The engine shuts off because it can't hover, and it drops like a stone onto the concrete.
Which brings up a brilliant distinction made in Aaron Rose's article regarding how we, as observers, perceive this landing.
How so?
Well, we watch the video feed, and we think we are witnessing a display of flawless, millimeter-perfect precision. But the author notes that this precision is essentially an illusion.
Explain that, because, I mean, it looks pretty precise to me.
It looks that way, but the software isn't actually searching for perfection. It isn't trying to land on a dime at exactly 0.000 zeros per hour. It is looking for a tolerance window.
A tolerance window.
Yeah. The 4 landing legs deploy at the last moment, significantly widening the rocket's stance to give it a broad center of gravity.
Right, so it doesn't tip over.
And more importantly, those legs contain crush cores. They are shock absorbers designed to permanently deform to soak up the kinetic energy of a hard touchdown.
Oh, so they expect it to hit a little hard.
Exactly. The rocket just needs to arrive inside a mathematical volume of acceptable error. The algorithms are constantly adjusting the throttle and the grid fins not to be perfect, but just to stay within survivable parameters. The article phrases it beautifully, actually. It says, "Precision is an illusion. Controlled error is the reality."
Controlled error is the reality. Wow. So the rocket is constantly messing up slightly, sensing the error, and fixing it. Messing up, fixing it. All the way down to a survivable thud on the crush cores.
That's a great way to summarize it.
We've deconstructed the mechanics now. We've successfully navigated the vacuum, the plasma, and the hover slam to get this building back onto the pad. But let's bring it back to you, the listener, and why this matters for the future of humanity in space. I want to return to that uncanny feeling we talked about at the very beginning.
Yeah, that visual glitch.
Right. So what does this all mean? The reason watching a rocket land feels so weird is because it completely shatters our lifelong mental model. For our entire lives, we have been conditioned to view rockets as ballistic artillery shells. You light the fuse, it goes up, and it is gone forever.
It's disposable.
Exactly. But when a booster lands on its tail, it shifts from being a disposable munition into a vehicle. It breaks the mold of artillery and becomes a sci-fi ship.
And if we connect this to the bigger picture, the Falcon 9 is really just the opening act of this new paradigm. It proved the economic and physical viability of orbital reusability, but the future the industry is building right now moves far beyond just landing the bottom half of a rocket.
Right, because right now they only reuse that first stage booster.
Yeah.
The upper half of the rocket, the part that actually goes into orbit, still burns up in the atmosphere or becomes space junk.
Yeah, but the source outlines the next generation of spacecraft currently in development, most notably SpaceX's Starship. The engineering goal for Starship is a fully 100% reusable system.
The whole thing comes back.
Both the massive lower booster and the upper orbital ship itself are designed to return, and the complexity of returning an orbital stage is an entirely new magnitude of difficulty.
I can't even imagine.
It requires massive aerodynamic control surfaces, belly flop maneuvers through the upper atmosphere to bleed off orbital velocity, and vast arrays of thermal tiles.
And it's also not just a SpaceX monopoly anymore either.
No, not at all. The entire aerospace industry has realized that expendable rockets are a dead end. Companies like Blue Origin and Rocket Lab are aggressively developing and flying their own reusable architectures.
Because the ultimate goal here isn't just like a cool party trick for a YouTube live stream.
Definitely not. The goal is a complete cultural and economic revolution. The objective is to reduce the cost of launching mass into orbit by orders of magnitude.
Make it cheap.
Make it cheap and routine.
Right.
When you stop throwing away the vehicle, when you no longer sink tens of millions of dollars into the ocean every flight, you only have to pay for the propellant and the refurbishment.
Which changes everything.
It transforms spaceflight from a rare, monumental historical event into routine logistics. It makes space genuinely accessible to smaller businesses, universities, and eventually private citizens.
It makes going to Mars actually possible.
It makes the logistics of establishing a sustainable human presence on the Moon or Mars a tangible engineering problem rather than an economic impossibility. We are fundamentally beginning to treat orbital rockets the way we treat passenger aircraft.
That is such a massive leap. From discarding multi-million-dollar masterworks of engineering into the salty ocean, to trusting a robotic brain to guide a 12-story structure through the fiery chaos of re-entry and hover slam onto a tiny concrete square.
It's incredible.
It is a profound testament to human ingenuity. And the wildest part to consider, as the article mentions, is that while this visual looks uncanny and magical to us right now, the next generation is going to grow up thinking this is just how it works.
They won't even bat an eye.
Right. To them, a rocket landing on its tail will be as normal and routine as the plane landing on a runway.
But this transition to aircraft-like reusability, this raises an important question for you to mull over as we wrap up.
Oh, what's that?
If rockets are now fully reusable vehicles rather than incredibly expensive single-use monuments, well, how will that fundamentally change the design of the cargo we send up?
You mean the payload itself?
Yeah. For the last 60 years, if it cost you $500 million just to put your satellite on a rocket, you had to spend $1 billion designing that satellite to be absolutely flawless.
Oh, because you only get one shot.
Exactly. It had to be perfectly miniaturized to save weight. It had to be constructed from insanely expensive exotic materials and engineered with triple redundancies because it had to survive a single do-or-die launch.
Right.
But if launch costs suddenly plummet to a fraction of what they used to be, and the frequency of launches skyrockets, that entire design paradigm flips.
That is a fascinating shift in logic. If the FedEx truck delivering your package is reusable and cheap, you don't need to construct the cardboard box out of titanium anymore.
That's exactly it. If you can afford to launch 10 heavy, cheap satellites for the price of launching one miniaturized, perfect one, engineers won't need to spend billions over engineering spacecraft. We could enter an era of mass-produced, heavy, modular orbital infrastructure, just fundamentally changing the economy of space itself.
Wow. The sky isn't the limit anymore. It's really just the starting line.
Yeah.
Thank you so much for joining us on this deep dive into the returning rocket. Until next time, keep looking up, keep asking questions, and never stop wondering about the mechanics behind the impossible.